Wilczek is a 2004 Nobel Prize winner in physics for work he completed as a graduate student, and the Hermann Feshbach Professor of Physics at MIT.
The book, A Beautiful Question, is a long meditation on this question. Does the world embody beautiful ideas? That question has two sides. On the one hand, the world. What is the world? And secondly, what is beauty? It may seem like a nebulous, vague, woolly kind of question, but actually properly understood, it can be made quite precise. What is the world? We address scientifically, and over the course of the 20th century, after a long development, we've understood a very important aspect of that. What are the fundamental laws that make the matter around us work? And on the other hand, what is beauty? Beauty is famously a subjective and elusive concept. Nevertheless, we can address empirically the question, what is beauty, by examining the historical record of what people have found beautiful. And then we can see if there are correspondences, if there's any overlap between the basic concepts that emerge from the description of the world and the human conception of beauty. So, as is documented in detail in the text, two dominant themes emerge from our fundamental world description: symmetry and exuberance. Both of those are used in a special sense in science, and as it applies to the fundamental description of the world. Symmetry means change without change. That may seem like an odd, almost mystical concept, but it's actually quite precise and also very flexible. Think about a circle. It's clearly what you would think of as a very symmetric object. And it matches this definition because if you have a circle, you can rotate it around its center, which changes the position of every single point on it, but doesn't change the circle as a whole. So there are changes you can make that don't change it. If you take some arbitrary triangle and rotate it, no matter what you do, it'll always look different. If you take an equilateral triangle, which is somewhat symmetric, you can't rotate through an arbitrary amount, but if you rotate a third of the way around, 120 degrees, it comes to look like itself. So it has some symmetry, not as much as a circle, but some. You can apply the same concept to laws. Can you look in the different way at fundamental laws and still get the same behavior? For instance, in the theory of relativity, you learn that if you look at the world moving past it at a constant velocity, it still obeys the same laws as if you're not moving. So there are changes you can make without changing the fundamental laws. And the same concept also applies to equations. You can have the equations which encode the laws and ask if they admit kinds of transformations that change the meaning of the different symbols, but don't change the content of the equations. And we find the laws and the equations that are embedded in the fruition of our fundamental description of nature are extraordinarily symmetric. In fact, that's how we guess them. Nowadays, the frontiers of physics are so inaccessible, having to do with very small things or very large things. The easy stuff has all been done. It's not possible to just collect data in this old Baconian style and gather more and more information and just encode it in equations. The practical thing we've had to do is guess and then try to draw consequences from our guesses and see if nature agrees with our proposals. And in making those guesses, one of our main inspirations is trying to beautify the description of the world. And it's worked for me several times. Exuberance is a non-technical word that corresponds roughly to the idea of that you can get a lot out of a little. that you get out more than you put in, or that there's an emergent complexity. So again, that's our feature. That's a great feature of our fundamental description of the world. We start with a complete description of the elementary events, which is, as I mentioned, highly symmetrical, so at least conceptually simple, although it takes a while to learn how to deal with that simplicity. And from that description, we learn that one can build up chemistry of enormous complexity, enough to support metabolism, enough to support genetics, or in other directions, nuclear physics and astrophysics. So the laws have this property of exuberance. They look simple, but you can put them together to make complex, rich objects. So that's the picture that emerges, the main features, the striking features that emerge from the fundamental description of the world. Let's compare that to what people have found beautiful historically. So take a look at this. It's exuberant, and you see that it's many, many little symmetric pieces, triangles and circles put together. So exactly the same things are what people have found beautiful and in fact have thought of as their approach to the divine. In fact, it's almost uncanny, the concept of local symmetry, that you can make different kinds of transformations at different places in space and time, is what leads us to the precise equations, the tremendous amounts of symmetry that are the ones that successfully describe nature. And here too, you see, if I want to display the symmetry of one triangle over there, I have to rotate around its center. Another triangle over there, I have to rotate about its center. Those are different transformations, so you have to be able to change the transformations from place to place to display the full symmetry. Here's another example of symmetry and exuberance. Historically, a great discovery of Brunelleschi around 1420, which for me is the beginning of the scientific revolution, although that's often dated to Copernicus more than a century later. The discovery of perspective, how to accurately draw three-dimensional scenes on two-dimensional canvases, the way they actually look, was a fantastic description, a fantastic achievement. It's not usually thought of as a description of symmetry, but in a higher sense it is, which I'll tell you momentarily, and it's in this sense that we use it also in our fundamental descriptions. The idea of perspective is that you want to be able to represent the same reality from many different points of view. What possible images could correspond to an underlying three-dimensional scene? Now, suppose you've understood all that, what the possible images are that correspond to a given scene. You have a totality of possible images, and now if you move your object or rotate it, make those kinds of changes, although the object changes and its look from any particular vantage point changes, the whole collection of possible looks doesn't change. So when you've understood perspective, you've understood symmetry. You've understood a way of making changes without change. And you can see that the discovery of perspective was a tremendous catalyst for driving the Italian Renaissance. Very shortly after Brunelleschi's discovery, people like Perugino, who drew this one, were having a great time with perspective. You can see you can see the joy he had in being able to draw this city square accurately. Even the people in the city square are really happy that they are in something that's drawn accurately. And you fill it with buildings so you can draw them accurately too. So it is something that people have found beautiful. perspective, symmetry. It's also, if you think about it, a form of relativity. You can look at the things in different ways. They represent the same information, equally valid, but the appearance is different. And finally, in our little history of art, we have this by Matisse, which is a different kind of symmetry, one that's also uncannily represented in our fundamental description of nature. What Matisse is doing here is changing the sense of color in different places. So in one place he's rotated green into red, in another place he's rotated red into purple or whatever. You can see he's playing with the colors. In our fundamental description of nature, this kind of possibility of making transformations at different places in different ways is absolutely fundamental. That's how we guessed and correctly guessed the fundamental laws, specifically of the strong and weak interactions. Okay, so that's the demonstration with evidence that the world does embody beautiful ideas. Now I'd like to pass to the second part of this discussion, which is a short reading. This reading is from close to the end of the book, so it refers in a few places to things that came before, but it doesn't lean heavily on them, so I hope you'll find this tantalizing rather than irritating.
Microphone.
Okay. So, trust in beauty has often in the past paid off. Newton's theory of gravity was challenged by the orbit of Uranus, which did not obey its predictions. But Urbain Le Verrier and also John Couch Adams, trusting in the beauty of the theory, were led to propose the existence of a new planet, not yet observed, whose influence might be responsible. Their calculations told astronomers where to look and led to the discovery of Neptune. Maxwell's great synthesis, as we've seen, predicted new colors of light, invisible to our eyes, not yet observed. Trusting in the beauty of the theory, Hertz both produced and observed radio waves. In more recent times, Paul Dirac predicted, through a strange and beautiful equation, the existence of antiparticles, which had not yet been observed, but soon thereafter were. The core, our fundamental theory, anchored in symmetry, gave us colored gluons, W and Z particles, the Higgs particle, the charm quark, and the particles of the third family, all as predictions prior to their observation. But there have been failures too. Plato's theory of atoms and Kepler's model of the solar system were beautiful theories that, as descriptions of nature, utterly failed. Another was Kelvin's theory of atoms, which proposed that they are knots of activity in the ether. Knots come in different forms and they're not easily undone, so they have, it might seem, the right stuff to make atoms. Those failures, in quotes, were not without fruit. Plato's theory inspired deeper study of geometry and symmetry. Kepler's model inspired his great career in astronomy, and Kelvin's model inspired Peter Tate to develop the theory of mathematical knots, which remains a vibrant subject today. But as theories of the physical world, they are hopelessly wrong. The fate of supersymmetry is not yet decided. Its discovery would, as I've described, reward our trust in beauty as a guide to deep reality. There are good reasons to think the discovery may be imminent, and beautiful reasons to hope so, but it has not yet occurred. We shall see. According to the story of doubting Thomas, the Apostle Thomas was skeptical of Jesus' resurrection, withholding his belief in the absence of evidence. And here is a quotation. "Except I shall see in his hands the print of the nails, and put my finger into the print of the nails, and thrust my hand into his side, I will not believe." When Jesus did appear to Thomas, he allowed Thomas to examine his wounds, and Thomas believed. And Jesus said, "Thomas, Because thou hast seen me, thou hast believed. Blessed are they that have not seen and yet have believed. That story has inspired many works of art, including Caravaggio's Incredulity of St. Thomas, the one you see here, which I find resonant. To me, Caravaggio's rendering conveys two profound messages that go beyond the words of the Gospel's text. One sees, first, that Jesus does not resist Thomas's inquisitive examination, but rather welcomes it. And one sees that Thomas is fascinated and excited to discover that reality conforms to his deepest hopes. Doubting Thomas is a hero and a happy man. Those who believe without seeing are blessed with the joy of certainty, but it is a fragile certainty and a hollow joy. Those whose faith is not passive, but engages reality, will receive a second, more fulfilling blessing in the harmony of belief and experience. Blessed are those who believe what they see. Thus endeth the sermon, and we move on to part 3. This is my favorite physicist. This is a picture of James Clerk Maxwell in his prime. And you can see something of his spirit here. He has a gleam in his eye and a little grin in his face, and he's holding a toy, like a playful little kid. But what is this toy? It's a strange-looking toy. That toy is actually a scientific instrument. It's a color top, which Maxwell used to elucidate the nature of color, or our perception of color, I should say, quantitatively. So here's the sort of thing that might have gone onto the top of the top. You have two bands, circular bands, which you put different colors, strips of paper on. Okay, so the picture makes that clear, I think. And you can put different colors in the different bands. What Maxwell did was show that he could produce, and then you can spin it around and see if the colors match, see if the perceived colors match. What Maxwell did is show that in a long series of experiments extending over many years, in which his wife played a big role, that he could match the perceived color of any strip on the outside using just 3 colors on the inside with different lengths. This is called trichromatic vision. It's what humans have. And it's the basis of computer displays, color photography, color movies, all the technologies of color in practice are based on having 3 kinds of sources that you mix and match in different proportions. That allows you to get any perceived color. When in a computer you see millions of colors, that just means different proportions of 3. So here, for instance, you can see that you can get perceptive yellow, the perception of yellow, from a mixture of pure green and pure red. Even though physically it's quite different from the yellow of the rainbow, which is a pure color itself, the perception of it is identical. So we can capture that geometrically in an appealing way with the idea of a color cube. So in one direction you have the intensity of blue, in another the intensity of green, in another the intensity of red, and by cranking the intensities from 0, where they're all 0, you have that black corner, to up there where they're all maximal, you have a white corner. You get every color, every possible perceived color in between represented uniquely in the color cube. So color, our perception of color, is a 3-dimensional space. Keep that in mind. There's no denying the mystical appeal of the concept of extra dimensions. It's appealed to mystics for thousands of years and appeals to people today. You can see pictures like this. in books about the frontiers of physics and speculations about extra dimensions, where you have extra structure, extra dimensions folded on top of the dimensions of space or space and time. Really looks tantalizing and fun. But those dimensions are very small if they exist at all. Wouldn't it be marvelous if we could experience extra dimensions? What would that be like? Well, we can, and we do. So here's our friend the color cube. And now if you think about what's being displayed in a computer display, at every point on the screen, you have to pick a point in the color cube. So actually it's sampling almost exactly the same kind of space as that mystical vision you saw before. We can describe this also mathematically, or more formally, no equations, but formally, I hope you forgive me. If you're a computer, or if you're programming a computer, what do you need to tell to know exactly what to do, exactly what to output? Well, you have to know at every time, t, at every position on the screen, x and y, how much red, how much green, and how much blue to output. So those are 6 numbers. The first 3 describe space-time. The next 3 describe this internal space, if you like, or this property space of colors. But they look exactly the same in the description. So a 6-dimensional space is what you're experiencing as you look at a computer screen. And the answer to the question, what do extra dimensions look like, is you're looking at them. This is a very fruitful concept. You can ask, what can I accommodate? More dimensions of color? Can I expand the doors of perception? And the answer is yes, and you'll see how to do it in this book. If I to explain the details, I'd have to get you to sign NDAs, but I'm not going to do that. Instead, I'll open things up for questions now. Thank you very much. The question is, okay, another aspect of Maxwell's work was to show that light is described by the Maxwell equations of electricity and magnetism, to the understanding he achieved, which is still basically the understanding we have today. The deep description of light is that it's disturbances in electric and magnetic fields. Those disturbances can have different wavelengths, and in fact, each different wavelength represents a different color in the rainbow. So really, physically, there's a whole continuum of different possible colors. It's just that our perception boils that continuum down just to a three-dimensional space. Other creatures see differently. So dogs, for instance, see a two-dimensional world. The way that works is perhaps most easily captured if you think about sensitivity curves of our different color receptors. We have in our eyes 3 different kinds of cones that are different sensitivity to the different possible colors. And their response is all or none, so they don't distinguish which color of light they're seeing, but their probability of firing depends on the frequency of the light. So there's a so-called blue receptor, which is most sensitive to colors towards blue, but really can also fire to things that are not blue in any real sense. And then there's a green receptor and a red receptor. Those are the 3 that humans have. Dogs have only 2, but before you feel too superior, you should know that there's a species called the mantis shrimp, or actually a family of species called mantis shrimps, that depending on which particular kind of mantis shrimp you're talking about, can have between 12 and 16 different kinds of receptors that have greater sensitivity in visible light. You can distinguish things with invisible light that we think, to our perception, look the same, but also they can have sensitivity to infrared. They have some sensitivity to, well, a lot of sensitivity to ultraviolet at short wavelengths. And they can also sense some polarization of light. They're the superstars of the visual world. And this is what they look like to us. It's fun to think about what they look like to each other. That presumably is what's driving their interest in color. They're doing displays and communicating somehow with their bodies. Anyway, this is an inspiration. And my philosophy has been, if the mantis shrimp can do it, we can do it. Oh, sound is very interesting too, and that's explored, I think, in fascinating ways in the book. The original scientific discovery to my mind was Pythagoras' discovery that the notes which sound well together, that make harmonious chords, in our present way of phrasing it, are the ones that have simple ratios of frequencies. So 2 to 1 is an octave, 3 to 2 is a fifth, and so forth. Whereas if things are a little bit off, that sounds horrible. So that's a kind of, that was a fantastic discovery. It's still not understood why it's true. But I have a theory of it, which is that, and which is very relevant to the sense of beauty, which is that, what is beauty? If you think about it from an evolutionary point of view, beauty is things we like to look at that we get rewarded for. There are many kinds of beauty. There's beauty of the human form, and it's obvious why that should be something nature rewards us to appreciate. There's moral beauty, but there's also beauty that comes from understanding the world better. And this is concrete. We face a tremendous problem perceptually in taking the input that we actually get and reconstructing from it a world. We need, in order to function efficiently, to understand that there's a three-dimensional world with objects in different places that we can navigate around based on our sensation, which is a two-dimensional projection on the back of our retina that's kind of all scrambled up. So it's not an accident that a lot of our brain, depending on how you count, between 20 and 50%, is devoted to visual processing. And we're very good at it, although we don't know how to do it. So, I mean, we don't know how we do it. So, although perspective was a late discovery in human history, we all do it unconsciously. We know, we can recognize that we're looking at the same object from different places. Anyway, but there are difficult problems that perception has to solve, and that's also true for sound. My theory is that evolution rewards successful learning of tricks to deal with these perceptual problems. And so the reason that we find these sounds that are in simple ratios appealing, beautiful, why nature rewards us for recognizing them, is that the wave patterns, the patterns of vibration in time that those represent have regularity, and from a small piece of it you can predict how the rest is going to work. And so when we do that and it works, that's beautiful. We find that we're rewarded for that. We find it beautiful. On the other hand, if they're slightly off, then we think we're going to be able to predict what's going to happen, but our prediction is wrong. So that's really horrible. So it's like when you play a C and a C sharp together, that it sounds really horrible when things are almost met, or C and the D. So it's when it looks good for a while, or when your piano is slightly poorly tuned, so things are almost right but not quite. That's what sounds the worst. So, so sound is very much something we can also try to understand, and gives great insight into, I think, the nature of why we find some of the things we do beautiful. Basically, the insight is we find things beautiful that we can learn from, that we can learn how to get around in the world successfully using. So understanding the world properly is a beautiful thing for good evolutionary reasons. Well, what I've stressed in this book is the use of images, especially, and also use of musical ideas, and also a historical approach. So, talking about the evolution of ideas going way back to Pythagoras and Plato, because the evolution of you can see where the ideas came from, how they had to be modified, how they evolved, and that makes them seem much more natural and compelling, like building a narrative. People love narratives.
Do you have any comments on Herman Weil's sort of mischievous suggestion that if he had to choose between beauty and truth, he would pick beauty every time?
Yeah, Herman Weil is a great hero of mine, and is also very much present in this book. And I grew up scientifically and philosophically largely on Herman Weil's books, so I'm a great admirer. And I think that's an honest description of himself, if chosen. Because he was a mathematician more than a physicist, although he did make important contributions to physics. So yes, it's possible. For mathematicians, it's very common to prefer beauty to truth. Physicists try to have it all, and they feel, what I like to say is trust but verify. So we trust in beauty to motivate our guesses, to guide how we might make progress, but the process is not complete until, like doubting Thomas, we actually poke and see that it's right.
What they're doing is they're picking parasites off, any debris or detritus or anything like that that accumulates, and you can even see these guys swimming into the gill slits of the manta for a deep clean.